Yeah, so we were discussing about the definitions. Gain margin, amount of open loop gain that can be added to the system till the system becomes unstable. That means currently the system is stable, and what is the margin in open loop gain that can be added to the open loop gain so that the system goes on the verge of instability. Okay, so that is gain margin. Same is the definition for phase margin, but only for considered for phase. Instead of adding the gain, you can add some phase angle till the system becomes unstable. Okay. Gain crossover frequency is the frequency at which the magnitude plot crosses 0 dB. Now, what is the significance of this 0 dB? Usually we have seen that when we have the characteristic equation 1 plus GSHS equal to 0, then in that case we have seen in the root locus also magnitude condition is magnitude of GSHS must be equal to 1 and angle of GSHS must be equal to plus minus 180 degrees. So those concepts are incorporated in this Bode plot, where the frequency at which the magnitude crosses 0 dB, that means magnitude is exactly equal to 1. Now, why it is equal to 1 and what is the significance of 0 dB? If you calculate the magnitude using the formula 20 log of K, when K is equal to 1, suppose open loop gain is equal to 1 of the transfer function, then ultimately the magnitude in dB is going to be 0 dB. So the frequency at which the magnitude plot crosses 0 dB, that is nothing but magnitude is equal to 1. That frequency is known as gain crossover frequency. We denote it with the help of omega GC. GC stands for gain crossover. And similarly, we have phase crossover, the frequency at which the phase plot crosses minus 180 degrees. Now, why are we considering minus 180 degrees? Because the systems that we are analyzing are mostly stable systems. And if you start solving problems, you realize that you get the angles where the angles or the phase is negative. If it is positive, then that type of systems can be analyzed separately, which we will not be doing so in our curriculum. So we encounter the problems or the systems where the phase is equal to or less than greater than minus 180 degrees. So that is why when the phase plot crosses minus 180 degrees, the frequency is known as phase crossover frequency. And now when both gain margin and phase margin are positive, then the system is stable. Even if one of these two is negative, the system is still unstable. Okay, so this is the relationship between gain margin, phase margin, and stability of the system. Now let me just explain exactly what do we mean by gain margin and how can we relate it to the concepts that we have already learned. Okay, so suppose now we have a root locus. I'm taking a random example of root locus. So here we have with this root locus, and now suppose we know that the value at this point, because root locus is plotted for various values of K, right? So value of K at this point we are supposed to find, and value of K at this point. Now, do you remember this is nothing but K marginal, because whenever it crosses the imaginary axis and it enters into right half of S plane, the system is unstable. When the root locus is in the left half of S plane, the system is stable. So we calculate marginal value of K where it crosses the imaginary axis. Okay, so this is say marginal value of K, and now for a particular example, suppose that value is 100. Okay, and at this particular random point, this point can be taken anywhere. I'm taking it randomly at this point. Suppose at this point the value of K is 50. Okay, so now what is the margin in gain that can be added to the system till it becomes unstable? We have 100 minus 50 equal to 50, right? So when K is equal to 100, after that when it increases, after that the system becomes unstable. Before 100 the system is, or till equal to 100, the system is still stable. So there is a margin of K equal to 50 that can still be added to the system. Still the system will remain stable, or we are pushing the system towards instability by adding some margin to it. Okay, exactly, this is the definition of gain margin. Gain margin is nothing but the amount of open loop gain that can be added to the system till the system becomes unstable. I hope this is clear now. Same is with phase margin, and we have seen omega GC and omega PC as well. Please understand, gain crossover occurs when magnitude plot crosses 0 dB. That means actual magnitude is 1. In dBs, it becomes 0. And in phase crossover frequency is frequency at which phase plot crosses minus 180 degrees. Okay, and when both are positive, this system is stable. Okay. Now, before starting with the next point, just let me know whether you have understood the definitions or not.
Yes, ma'am.
Okay. So now let us go to the example. Okay, listen everyone, please unmute yourself, all of you. Okay, now what I have done is, this is still not the perfect way of teaching or showing how to sketch the Bode plot. But as you also do not have semi-log papers and I also do not have semi-log papers, what I have done is, I have drawn the handwritten plot. I'll explain how it works and how it can be plotted. And what I have done is, I have run the code in MATLAB also, and I have taken the screenshot. So I'll exactly show how actually it is plotted, and we can relate it to the handwritten one. When you are solving the problem yourself, you will need to use the semi-log paper. On normal paper, you will not be able to plot it. Just for explanation purpose, I have done it so. Okay, is that fine? Shall I proceed?
Yes, ma'am.
Okay, so now I'm directly going to the problem. I have plotted the Bode plot for the same problem which we have discussed yesterday, and the transfer function was, do you have the problem in front of you, or do I need to show it to you again? Just a minute. Yeah, so this is the solved example. Yesterday we had solved an example where the value of K was 10, then the corner frequencies were 2, 5 and 10, and there was a pole at origin. Okay, so now if you have, you can please put the magnitude table in front of you, or shall I show it to you again? Just let me know, please.
We have that.
Okay.
I have that.
Yeah, okay, okay. So now the grid that is shown in the background is not the proper one. I have just plotted it for the sake of converting it into semi-log paper. Now what semi-log paper has, semi-log paper will have various partitions. Okay, yesterday we have discussed about decades. Okay, so those decades are represented in terms of those partitions in the semi-log paper. So I have randomly partitioned into various decades, and here on the x-axis you can see that the frequency is log of omega. Okay, so on x-axis we have a logarithmic scale. Then each decade will be represented. Now the first decade, as you can see, is the smaller portion, only this one, 0.1 to 1. Only this one is the decade. As we have a logarithmic scale, the partitions will not be uniform. the distance between two values, or for a decade, the partition span might differ. Okay, when you see the semilog paper, you will realize it. You can check it online also. You will get to see the example of semilog paper. So these are the partitions, 0.1 to 1, then 1 to 10 is another partitions. What I have written in between here is between 1 and 10 on the semilog paper, you will get 10 lines. Okay, and on top of it here, you will get to see it is written 1, 2, 3 up to 10. Okay, so between 1 to 10, you will find 10 lines. Between 10 to 100, you will find 10 lines. Now after 10, this first line that you have will be 20. Okay, then 30, 40, 50, 60, 100, then 200, 300 up to 1000. Okay, and between 0.1 to 1, we have 0.1, 0.2, 0.3, 0.7, 0.8, 9, 0.9 and 1. So this is how it is partitioned. Okay, now the very first thing is to sketch the magnitude plot. Okay, for magnitude plot, the very first thing that you can see, no, okay, basically here I have sketched two different plots. One is highlighted with yellow color, that is the final plot that we have, but before that there is a reference plot that also I have sketched. There is no need to sketch it all the time, but I'll tell you why I have done so. Okay, so in our case, the value of K is 10. Okay, and now to plot it, now value of 10, K is equal to 10, and the actual magnitude in dB would be 20 log of 10, that is equal to 20 dB. I have written so on the right side. Okay, now your magnitude plot should have effect of K for all the frequencies, because it is independent of the frequency. Whatever frequency you are working at, the effect of K or open loop gain will be there. Okay, so wherever you are in the Bode plot or by sketching the magnitude plot, you will have to consider the value of K. In this case, in this particular problem, it is equal to 20 dB. We have calculated it by substituting value of K here, and we are using formula magnitude is equal to 20 log of K. So that comes out to be 20 dB. Now this effect of 20 dB has to be there on this whole plot. But initially there are two ways to sketch it. From beginning only you consider this, or what I have done is I have sketched a reference plot, okay, which is unmarked. This is considering K is equal to 1. Okay, so when K is equal to 1, its magnitude in dB is going to be 0. So 20 log of 1 is equal to 0 dB. So here we are considering, for reference plot, we are considering that value of K is equal to 1. We will add the effect of K in the end while plotting it. Okay, so now just concentrate on the plot which I am just showing right now. Okay, I am highlighting. Now this yellow one is the final plot. Just ignore it for a while. And now before starting with the plot, what we did is your magnitude table's last two columns, net slope as well as frequency range. These two columns help you in sketching the magnitude plot. Initial first factor is 10. We do not have net slope, we do not have frequency range, because